Okay, so now we are still talking about the basic concepts and the main things that we need to know that have a lot of applications in the field of mass transfer. And one of them is the vapor pressure. And for the vapor pressure, it's a term that we use a lot, and it's like used in many things. We saw it in distillation, and we see it a lot in many other mass transfer operations and processes. But I would like here to give more information about the vapor pressure, just to have a better understanding of this term and its concept. So vapor pressure, it's important to know that it is a physical property that is specific for the material. So I know that if you tell me that there is a liquid that has density of 1,000 kilogram per meter cube, I will tell you that this is water. And I know this because I know that the density is specific for water. This value of density is specific for water. So if I have another fluid that has different density, I can look it up. I can see what is the fluid that has this density, and then I can tell you that this is the fluid. So this is a specific property for the materials. The same applies for the heat capacity, same applies for viscosity, for surface tension, for any other physical property of a material. So this applies also to the vapor pressure. And the vapor pressure represents the pressure that the fluid exerts on the surroundings. So if you have a cup of water, for instance, then the water tries to apply pressure on the surrounding, and there is some water vapor on the surface of the water. And at the same time, there is a pressure that's applied on the water from the surrounding, which is the atmospheric pressure. And the atmospheric pressure at normal conditions, at the normal temperature, the atmospheric pressure is higher than the vapor pressure of water, so water cannot compete with it. So it's kind of staying in the liquid phase because of the difference in pressures. Um, the vapor pressure is highly dependent on temperature. So if the temperature increases, then the vapor pressure will increase as well. And there are many equations that represent this, and one of the most famous equations is called Antoine equation. Antoine equation is in this form that we see here. It says that Lin vapor pressure equals A minus B over C plus D. A, B, and C are three constants that are dependent on the material. So there are tables that you can look up and see for any material, any liquid. You can look it up and see what are the values of A, B, and C. And from these values, you can substitute with any temperature, and you get the value of vapor pressure. What we have here in this graph is an example of the dependence of the vapor pressure on temperature. We have here four graphs, one for ethylene glycol, or for lines, one for water, one for ethyl alcohol, and one for diethyl ether. There are many observations that we can get from this graph. The first is that for all the graphs that we have, for the full graphs, and for any other graph that or line that you would put here for any other material, it's gonna increase with temperature. No matter what is the material that you are dealing with, its vapor pressure must increase with temperature. The second observation is that they don't increase with the temperature with the same rate. So here you'd see the diethyl ether increases quickly with temperature. So it was 200 and reached almost 1,000 in only 40 degrees Celsius difference. For ethyl alcohol, it increased from almost like 20 or 30 up to 1,000 almost, with 80 degrees difference in temperature. For water, it took more. For ethylene glycol, it's taking more and more temperature to reach this point. So each material has a way of being dependent on temperature that is different from the other. The last observation here is that you'd see the scale for the y-axis is 200, 400, 600. So it's 200 millimeter mercury or torrs step. But here it shows the 760, which is 1 atmosphere, 760 millimeter mercury or torrs. And from this you would see that for diethyl ether it's 34.6, for ethyl alcohol is 78.3, for water it's 100. And we know that for water the 100 degrees Celsius is the boiling point, or the normal boiling point. This is what we say. And from this we can understand why water evaporates in the normal conditions at 100 degrees Celsius, and this is because the vapor pressure of water at 300 degrees Celsius equals the atmospheric pressure. So water can now push the air with the same pressure that the air is pushing it. So it now has enough energy to push the air and leave the liquid phase and go into the vapor phase. And this is the basic theory of evaporation, is that the evaporation of any liquid takes place when the vapor pressure equals the applied pressure, no matter how much is this or how much is this. So if I increase the outside pressure, then I have to heat water to higher temperature until the vapor pressure reaches that vapor pressure. So this is an important concept, and this video is a nice video that describes this concept well. In this video, we have this man. He has a setup here. There is a glass flask. It's sealed, it's closed, and there is a tube here that's connected to a vacuum pump. There is this pressure gauge that shows the pressure inside. So if we take a look here, I'm just gonna skip this part a little bit. So this is how the pressure is in the beginning. It's almost 14.7 millimeter mercury, which is PSI, which is 1 atmosphere. And now he is going to turn on the vacuum pump. So he is reducing the pressure on the water. You see water is at room temperature. He is not applying any heat. And what's gonna happen now is that the pressure is decreasing. This is what we saw in the pressure gauge. And what happens here is magnificent. You can see water is boiling. It's literally boiling. At room temperature, he is touching it with his hand. He doesn't feel any heat, but it's boiling now because the applied pressure is getting lower and lower until it reaches the vapor pressure of water at the room temperature. And that's why from this graph you'd see this, it says it says normal boiling point. So normal boiling point is the boiling point at normal pressure, which is 1 atmosphere. So this is like an important concept to keep in mind. Now, since we are talking about mass transfer, we need to shift gears to a new concept, which is an important concept actually, which is the velocity of motion. So since we already have transfer of mass from a point to another, and we have like different species. You might have 3 or 4 different compounds that are diffusing from a point to another. There are many reasons that these species will diffuse in different velocities. So it's important to talk a little bit about the velocity of motion and how we deal with different species diffusing with different velocities from a point to another, because this is an important concept and we see it a lot in mass transfer. And this is the basics or the basis of the separation in general, that you have different species diffusing with different velocities, so you can control. If you can control this, you can separate them easily. You can get one to go to one place while the other is not diffusing. So this is important. And since the velocity of motion is one key parameter here, then we will talk a bit about it. And just to make it easier for us, I will give a simple example for something that we are very familiar with, which is car race. So let's say we have 3 cars that are going on a race, and they are first staying here. They are ready to go to get going. And let's say you are the cameraman, and you have a camera mounted on a drone, and this drone is flying over the cars. It's very fast drone, so you can control easily the speed of the drone with a remote controller. And you are asked to record the race, and what you're supposed to do is to make sure that the 3 cars are in the video. So you have to move the drone so that you have the 3 cars in the screen, so you don't miss any one of them. So this is what you're gonna do. So the race started and the three cars are running now, and they are running, of course, with different velocities. This red car is the fastest one. The yellow is the poor slow car, and they are going with the velocities that we see here: 155, 170, and 180 kilometers per hour. And you are now recording the race, and you are controlling the speed of the drone that's flying over the cars to record them. So you're thinking, what speed shall I control the drone to fly at? So I should I fly the drone at speed of 180 kilometers per hour, or shall I make the drone fly at speed of 155 kilometers per hour like this guy? So let's think about it. If you let it fly with a speed of 180 kilometers per hour, then you are getting this car in the video, but this car will be out of the screen after some time, because this is not fast enough. So you will see this, and this is not gonna be visible. And if you go the other way, then you would keep this in the screen, but this is gonna go fast and leave, and you will not be able to see it. So the simple logic that you will think of is, okay, I'll go for an average velocity. So the average velocity is gonna be the average between the the velocities of all the cars. It's gonna be, let's say, something around 165 kilometers per hour. For example, let's say it's 165 kilometers per hour. So this is the velocity of the drone that you are that you are controlling, so that it flies over the three cars and records the race. And now, for you as the person looking at the camera or the recording in the drone, what velocities that you will actually see? Is it 170, 180, and 155 kilometers per hour? Of course not, because the drone is going with the speed as well. It's not stationary. So the velocity that you will see actually is the relative velocity, and this is the point, that there is a relative velocity, and this is going for you. This is gonna be going with 15 kilometers per hour because you're going with 165. This is gonna go with 5 kilometers per hour because it's 5 kilometers per hour faster than you are, and this is gonna be negative 10 kilometers per hour. So this is what happens when you are recording the velocities, and this is what you will see, which is not the actual velocity, but is the velocity relative to your velocity or the drone's velocity. And once the race is done, then this guy who is holding the flag is standing here, and he is looking at the cars while they are crossing the line. So the velocity that he is observing is the actual velocity of the cars. So he is seeing that this, because he's standing in his place, he's not moving. So he sees 170 kilometers per hour, 180, and 155 kilometers per hour. So from this we can reach a conclusion that there are two ways to notice or to describe the velocities of the three cars, depending on the reference. If you are recording the velocities with reference to their average velocity, then this is one way. The other way is to record or describe the velocities with respect to a stationary point, a point that is not moving. So this is the other way of representing the velocity. So we can apply the same thing for the diffusion, let's say, in gases. So if I have three species and they are diffusing from a point to another, there are many reasons for these three species to diffuse from a point to another with different velocities. This can be a result of the difference in the driving force. One of them might have a higher concentration difference than the other, so it will have higher driving force. It can be a result of the physical properties of the material itself. It can be one of them might have higher molecular weight, so it's harder for the molecule to go from a place to another. It might be a result of the molecular volume. It's a huge molecule, so it's not easy for the molecule to go from a point to another. It might be due to the bonding that is there between the molecules of the material. They might form bonds, and this makes them makes it more difficult for them to move. So again, there are many reasons that will make the species diffuse at different velocities. So this is exactly what happens, very similar to what happens in the car race. So what we see here is exactly like what we see in the car race. And in this case, we can describe the velocity of the gas mixture. They are all moving, so we average the velocity. You can get an average velocity of these three components, and this average velocity is very similar to the average molecular weight. You can put the average with respect to the mass. So I can say that I have three species. One of them represents 90% of the whole mass, and the other represent 10%. It's like what we saw in the previous case in case of hydrogen and carbon dioxide. Or you can say, no, I'm gonna do this with respect to moles. So I have one species with larger number of moles, so I'm gonna average with respect to the number of moles, not the mass. So the way we do this is we calculate the summation of the mass concentration. If this is the mass average velocity, then it's summation of mass concentration multiplied by the velocity, which is the actual velocity, and then I multiply this by the summation of the mass concentrations, and you can and the summation of mass concentration is the density, so this is gonna be the mass fraction. So this is one way of representing this, is that the velocity, the mass average velocity, equals to the summation of mass fraction multiplied by the actual velocity. So this is one way. The other way is the molar average, which is as the mass fraction. We will replace the mass concentration with the molar concentration, which will end up with xivi, or summation of xivi, or summation of yivi, which is the mole fraction in gas or in liquid phase. So this is how we can represent the mass average or molar average velocity. There is one important thing to notice here, which is that we described, or we put the term for the actual or the average velocity for the mass average velocity as the lowercase v, or small letter, and for the molar average velocity with the capital or uppercase letter. And this is something that we will do a lot in this course from now on, is that if we have the same term for mass or for moles, then we will put the mass in lowercase letter and the mole in uppercase letter. So this is important, so please keep this in mind. So if we want to get the average or the velocity relative to the mass average or relative to the molar average velocity, then we will get the difference. It's like what we do in the like physics in the high school, that we get the velocity relative to the average velocity. So it's vi minus v, this is the mass average, or vi minus uppercase v if this is relative to the molar average velocity. The last thing we will discuss today is in this video, is the flux and the flow rate. We discussed this before, and we said that the flux is the flow rate divided by the area. The rate is the mass per unit time, or moles per unit time. So the flux is the mass or moles per unit time per unit area. And again, the flux, we give it the symbol lowercase j or uppercase j. Lowercase j if it is in kilogram per meter square second, uppercase j if it is in kilogram mole per meter square second. And again, as we did for the flux, we will do the same for mass, for the velocity. We will do the same for the flux, that we can calculate the flux, because it's a form of velocity as well. So you can calculate or describe the flux or define it with respect to, or with reference to, coordinates that are fixed in space, or coordinates that are moving with the mass average velocity, which is what we did in the case of the drone, or coordinates that are moving with the molar average velocity. So this is one thing which is pretty important. We will talk about it more in the future, and we will go through some mathematical representation of these terms. But just keep this in mind, that these are the 2 or 3 ways that we can represent the flux. So I'll end this video by this, and the next video we will start talking about the equations that describe the flux and the rate. So I'll see you then, inshallah. Goodbye.